Welcome back to Module 2. We are continuing Module 2 to understand the effect of different pulse shape if we consider, and what is the effect of different pulse shape on the time bandwidth product. We have to calculate time bandwidth product depending on what kind of pulse shape we consider. So far we have considered the Gaussian pulse, then we have considered a rectangular pulse, and we can just continue the way we are thinking. Assume we can also assume and a hyperbolic sec function like this, and hyperbolic sec function which is also centered at t equals 0 as an envelope to represent the ultrafast pulse. And many other envelope functions can also be used as shown here. So the Gaussian pulse envelope, then hyperbolic sec function, Lorentzian function, asymptotic sec function, hyperbolic sec function, many other field envelopes one can assume, and depending on the field envelope one can follow similar mathematical formulation and get the time bandwidth product for a particular pulse shape. Here we see that the envelope functions do not differ significantly if we change Gaussian to let's say sec hyperbolic, except for the wing. This is your temporal profile of the pulses. We see a major difference here in these wings, but in the spectral profile we see a major difference all over the spectrum. So depending on the experimental spectrum and experimentally measured intensity profile, one can assume a certain intensity profile or assume certain field envelope profile to represent the ultrafast pulse. We will continue this for the sec hyperbolic function, and which can be represented by this, and it can be shown easily that the time bandwidth product for transform limited sec hyperbolic pulse can be given by delta nu delta t equals 0.315. So we'll try to find out how we get this number. We know that this sec hyperbolic function is centered at t equals 0. So if this electric field looks like this, then intensity profile can be written as I naught sec hyperbolic square at. And from the definition of the pulse width definition, we know that this is if this is intensity profile t it, then I get the maxima, half of the maxima when t equals delta t by 2, because this is delta t, so this is going to be delta t by 2. So from the definition of full width half max of the intensity profile, I get I max equals I naught divided by 2, which is the maximum intensity divided by 2, which is nothing but I at t equals delta t by 2. If I plug that in, I get I naught sec hyperbolic square a delta t by 2. Or in other words, half equals sec hyperbolic square a delta t by 2. Or I can write down delta t equals 2 by a inverse of the sec hyperbolic function 1 by square root of 2. So this expression will keep it for future. We'll write it down. On the other hand, if we have time domain field, I can also express frequency domain field in a following way. E omega is nothing but the Fourier transform of the time domain field, which is Et e to the power minus I omega t. Procedure is the same. Mathematics can be little different. So then I can write down E naught multiplied by minus infinity to plus infinity sec hyperbolic function of At e to the power minus I omega minus omega naught t dt. I just plug this in here. And this is a standard Fourier transform. The standard Fourier transform goes like this. If I have fx, a function, hyperbolic sec function At, then the Fourier transform of ft is going to be pi by a multiplied by sec hyperbolic pi omega by 2a. So we can use this standard integral here, and we get E naught pi by a sec hyperbolic pi omega minus omega naught divided by 2a. So if we get the field in the frequency domain, then I can get the power spectrum in the frequency domain, which is nothing but S omega, nothing but E omega multiplied by E star omega, that we have to calculate. And if we calculate that, then we get S omega equals S naught, the maximum amplitude, and sec hyperbolic square pi omega minus omega naught divided by 2a. Again, this is centered at omega naught, just like a Gaussian function. So from full width half max definition, we know that we get the half of its maxima when omega equals omega naught plus delta omega by 2. So I can write down S naught divided by 2, half of its maxima we obtain when S omega equals omega naught plus delta omega by 2, which is nothing but S naught square of this hyperbolic function pi. Now omega, I have to plug in this one, omega naught plus delta omega by 2, that is my omega, minus omega naught divided by 2a. So this omega naught cancels out. So finally I get pi delta omega divided by 4a, or in other words delta omega. If I rearrange this equation, we get 4a by pi sec hyperbolic inverse 1 by square root of 2. So I have delta omega expression. In the previous slide I had the delta t expression, which was 2 by a sec hyperbolic inverse this. So to get time bandwidth product, I just multiply delta t delta omega. I get 2 by a multiplied by 4a by pi (1 by square root 2 whole square. If we simplify, then I get delta t 2 pi delta nu, which is nothing but 8 by pi. This value is going to be 881 whole square, or in other words, delta t delta nu is going to be 0.315. One can use calculator to recheck this expression. So what we get is that for hyperbolic sec function, time bandwidth product is going to be 0.315, which is different from a Gaussian pulse or a rectangular pulse. This table here is showing time bandwidth product, this CB, time bandwidth product of different pulses. If it is a Gaussian pulse, it is 0.441. If it is a hyperbolic function, it is 0.315, and many other line shapes we have, many other pulse shapes we have, and we can have different values. We have to remember that we have to assume a pulse shape first, then corresponding time bandwidth product we should use. We should not mix these numbers. For delta nu, delta t, if we assume that it is a Gaussian pulse, then I can write down this time bandwidth product for a transform limited pulse. And often we need to convert this equation to the wavelength or wave number, and we'd like to know how we can convert it. So this delta nu can be written, we knew that nu equals c by lambda, which is nothing but c nu bar, which is the wave number. So delta nu can be converted to wave number with the help of this expression. On the other hand, if we have to convert it to wave length, then we have to write down delta nu equals c by lambda square delta lambda. It's coming from this expression. There is a negative sign here, but we are omitting it. We are just considering the magnitude of this. So these are the conversions we should remember. If we want to convert delta nu to its wave number, this is the equation. And if we have to convert delta nu to delta lambda, then this is going to be the expression. So now we plug that in and we get that if I convert it to wave length, then I get c by lambda square delta lambda, sorry, this is lambda, delta t equals 0.441, or delta lambda delta t is going to be 0.441 multiplied by lambda square divided by c. This lambda in this equation, this lambda is going to be center wavelength. We call it, if it is 800 nanometer pulse, it is going to be 800 nanometer. So what we see is that delta lambda delta t will depend on its center wavelength, which we haven't seen before in the time bandwidth product. So we can use these expressions and we can take an example of 100 femtosecond pulse. We can consider 100 femtosecond pulse at 800 nanometer. We know the meaning of it now. 100 femtosecond pulse, it means that it is the full width half max of the intensity profile of the pulse. Center wavelength is going to be 800 nanometer. So if it is 100 femtosecond pulse at 800 nanometer, center at 800 nanometer, then delta lambda one can calculate with the help of that expression, 0.441 multiplied by lambda square divided by C, which is nothing but 0.441 multiplied by 800 multiplied by 10 to the power minus 9 square divided by 3 into 10 to the power 8 meter per second multiplied by delta T. So 3 into 8 meter per second multiplied by 100 femtosecond 10 to the power minus 15 second. So finally this will give me meter, and if we use the calculator we will be able to quickly get 10 nanometer. Please check with the calculator whether these numbers are correct. So delta lambda, the bandwidth in the wavelength for an 100 femtosecond pulse 800 nanometer at 800 nanometer is going to be 10 nanometer. So what does it mean? It means that I have center wavelength 800 nanometer, but its width is plus minus 5 nanometer. So this is going to be 805 nanometer and this is going to be 795 nanometer. So this is the spread of the spectrum which we see. On the other hand, for the same pulse, if we have to express, this is in nanometer we have expressed, now we want to express in wave number, centimeter inverse. In many occasions we have to use these conversions to understand the spread. That's why it is instructive to take an example. So we know that this same expression can be rewritten as delta nu bar delta T equals 0.441. We are assuming that we have Gaussian pulse. If we assume that it is a hyperbolic sec function, then this number will be different. But if we assume Gaussian pulse, then this delta nu bar is going to be 0.441 divided by C multiplied by delta T. We can plug that in, all the numbers, 441 divided by 3 into 10 to the power 10. Here we are considering centimeter per second into 10 to the power 100 femtosecond 10 to the power minus 15 second. So what I get is 147 wave number. Please check that number with a calculator. So what we see is that now if we plot it in the wave number regime, then delta nu bar, the width of the spectrum is going to be 147 wave number, and if it is delta lambda, then it's going to be 10 nanometer. So with this one can convert to different representations for the time bandwidth product. So what we have seen so far is that we have discussed different characteristics of an ultrafast pulse. In this module we have discussed how to calculate the frequency spread for a particular pulse, or frequency content of a particular pulse from the temporal duration. Or in other words, if I want to achieve a certain pulse duration, what would be how many frequency components we need, what are the frequency components we need, that we have discussed. And when we have discussed all these characteristics of the pulse, we have always considered that I have an isolated pulse. Now isolated pulse in any experiment will propagate through the medium. We use lens, we use crystal, we use wave plate. All of these materials are of dielectric nature. So we should understand the propagation of the pulse through the dielectric medium. Mostly two effects we observe when an ultrafast pulse propagates through a dielectric medium: the high intensity effect and large bandwidth effect. High intensity effects, when you say high intensity effect, we can consider 100 femtosecond pulse again, and each pulse contains, let's say, 100 microjoule energy. So with this 100 microjoule energy, now we can calculate peak power. The peak power is going to be can be written as 10 to the power 9 joule per second. One can calculate it quickly with the help of peak power equation. And if it is focused to, let's say, 200 micron diameter spot size, if it is focused to that, then what I get is peak intensity at the point where it is focused. That peak intensity is going to be almost 10 to the power 13 watt per centimeter square. This high peak intensity, if we consider sunlight peak intensity in a brightest day, is going to be let's say less than 0.1 watt per centimeter square. So we can compare sunlight peak intensity and the peak intensity one can achieve from an ultrafast pulse with a moderate energy. This 100 microjoule is pretty low energy, but very frequently used in the ultrafast laser spectroscopy lab. So which suggests that if we have a moderate energy pulse, that pulse can give me peak intensity of the order of 10 to the power 13 watt per centimeter square. It's a huge intensity, and because of that intensity we get polarization, we get nonlinear effects. So these are all related to the nonlinear effects. On the other hand, if we look at the large bandwidth effect, we know that there are many frequency components traveling through the medium, and it may so happen that the red component are facing different velocity than blue component, and that's why they will spread out. So always, due to large bandwidth, due to dispersion, the pulse duration will always elongate as compared to the due to the dispersion. So these are the two effects which we will experience when the pulses are propagating through the medium. We have come to the end of this module. We'll discuss all these high intensity effects and dispersion effects in the next modules. What we have studied here in this module is how to represent an ultrafast pulse mathematically, and how to get different characteristics of the ultrafast pulse with the help of mathematical formulation. These mathematical formulations defines different terminologies like bandwidth products, like pulse duration, bandwidth, Gaussian pulse, hyperbolic sec functions. All these terminologies will be frequently used in this course. We'll meet again for the next module.